The monostable configuration of the 555 timer, you could also call it the one-shot configuration, is the most interesting and useful of all of the modes of operation of this chip. Not only on its own, but also as part of larger subcircuits, even involving other 555 timers connected to it. But today, just the on its own part. Specifically, using it as a one-shot timer, such as you press a button, and the user can let go of the button, and it's going to stay on for a certain amount of time, such as a backlight. You could press the button for a backlight, and the backlight will stay on for a certain amount of time. Or for switch debouncing, which is essentially the same thing, except instead of a number of seconds, it's going to be a number of milliseconds or even microseconds. Probably milliseconds. Switch debouncing can go on for a little bit. But if you have a switch that's bouncing when you press it once, and then it's turning off and on and off and on with its bouncing, the timer doesn't care. The timer is just on for however many milliseconds, and then it turns off after the switch is definitely done with its funny business. The trick to this configuration is once you start the timing sequence, once you turn the timer on, it doesn't matter if you keep pressing the button, it's not going to affect the time. As long as the button is let go, when the timing stops, it'll turn off, no matter how many times you pressed it, no matter how long you pressed it, while the timer was on. We start out just like before. We have our positive power terminal and our circuit ground, no negative power. Connect the VCC or VDD pin there, and the ground pin there. Just like before, we're not going to use the reset pin because the timer is going to be resetting itself. We're going to trigger it, let it go, and we never need to manually reset. So we just tie reset to high to prevent the floating input just like before. And similarly, we will not be using the control voltage. The internal voltage divider will be just fine. So we use our standard capacitor to connect to the cont pin. And this just disables those two pins, just like before, for the astable configuration. So let that be hewn into your mind, and now I will erase it. The remaining 4 pins are what is interesting. First of all, our input, and I will go ahead and use a switch for this. Let's say we have our positive power, we have a pull-up resistor, we have a switch that's going to send a ground signal, and we connect this to the trigger pin of the chip. The way we're setting this up, it's going to be active low, because remember, the trigger pin takes its voltage and compares it to the internal, which in this case is going to be 1/3 of VCC or VDD. So when the trigger voltage pin falls below 1/3 of the positive, then it is going to turn the flip-flop inside the timer on, and the timing will start. So we use a pull-up resistor to keep it high, so it's not triggering, and then we do this. If you're using some sort of microcontroller, you would just connect it directly, logic, whatever. This is just if you're using a physical button, standard pull-up resistor. So there is our activation. That's how we turn it on. And that's all for that. That's how you use the circuit. The remaining 3 pins are the timing. Unsurprisingly, here comes another RC network. So our lovely RC network is only one resistor this time because we're not doing both directions. We're not charging and discharging back and forth as we were in the astable. We only need to go one way. So one resistor, one capacitor to the negative, and just like before, it's resistance times capacitance times whatever factor based on how we've constructed the particular circuit. In this case, for my Texas Instruments chip looking on my datasheet, this is 1.1. 1.1. So it's just 1.1 times R times C. That, and this is R and this is C obviously, R and C, 1.1 times resistance times capacitance is the duration of the pulse. And remember, no matter how many times I hit trigger, if I hit trigger and then I hit it again and again and again, as long as it hasn't elapsed this yet, it's not going to care. Hitting trigger again while the timer is on does not reset the time. You hit the timer, this 1.1 times R times C will always be longer than the time that your button might be pressed, the switch might be bouncing. If you're using this to, let's say, extend an input pulse, like if you have short pulses and you want them to be long pulses, you can just use this and it'll just repeatedly trigger, and the pulses have to be separated by more than this, because that gives it time to actually turn off and then on again. So you have to be letting go of trigger before this expires. So that's the time. How do we hook it up? The middle spot here connects to both discharge and threshold. And then your final pin, of course, is out. That's just your signal. Out is your signal. we don't have any feedback here. So this is it. We hook up VCC and ground pins. We deactivate the reset and control voltage pins. Out is output. The trigger is just active low signal, which we just used a pull-up resistor, or you can hook it up to a logic input. And then the last 2 pins, this is all it is. It's a single RC network hooked up this way. So let's say that the circuit is quiescent. Let's say output is low, and it has been for a while. If output is low, then discharge is open. Discharge is conducting and connected to ground. So this capacitor is going to be fully discharged. It'll have ground and ground on both sides, and nothing will be happening here at all. Threshold turns off the timer whenever the voltage on the threshold pin is greater than 2/3 of VCC, since we're not using control. Well, right now, the voltage at threshold is 0. It's below. The timer's off, so it's just doing nothing. All right, this is quiescent. It's doing absolutely nothing. But the point is, if we were to turn the timer on, threshold is low, so it's not going to just turn it right back off. So let's say we apply ground, a low voltage, a low signal, to trigger. So the trigger pin goes below the 1/3 of VCC trigger voltage, comparison voltage. That turns the output to high, but the voltage here is 0, so it's not going to just turn it right back off. So what happens is output is high, so discharge closes. Discharge is always the opposite of the output. Output is high, timer is on, discharge is closed, and my pin is weak. So now this is allowed to charge. You don't have access to ground here. This is closed off. And threshold is just reading the voltage. That's an input. So it begins to charge, and your R times C times 1.1. And as it charges, the voltage on this capacitor rises and rises and rises until threshold goes above 2/3 VCC. That turns the timer off. Now, why does triggering not reset the timer? If you trigger and the timer starts and you trigger again, why doesn't it change the timing? Because this is a flip-flop in there. Remember, inside the 555 timer, there's not just circuitry with feedback and a signal. You don't trigger, like I've shown you circuits before that would re-trigger. This one uses the trigger signal to set the flip-flop to high. And then it uses the flip-flop high signal inverted to close discharge. So discharge is getting a low signal on its base or gate, and that's coming out of the flip-flop. So until something changes the flip-flop, the latch, the flip-flop, it doesn't matter what you do on trigger. Trigger cannot turn the flip-flop to 0. Trigger can only turn the timer on. It cannot turn it off. Only threshold can turn the timer off. So until this voltage rises, until threshold is reached, the timer stays on no matter what you do, and it doesn't affect it at all. And that's literally it. One of the most powerful, and yet the simplest, hookup. It's just an RC network. And of course, as soon as the threshold voltage is high enough, the output goes low. This is back open to ground, and you'll notice there's no resistor, right? This capacitor discharges to ground, but there's no resistor there. That's a short circuit. It sure is, and that worried me too. But I have faith in Texas Instruments. Their data sheet for their chip very clearly does not have a resistor here. And that's why the timer turns off pretty much immediately, because there's a short circuit there. This capacitor just dumps, bam, and it's done. And you're back to 0 here in microseconds. So obviously, the chip is designed to handle that voltage through, or that power through the discharge. Just trust your datasheet. Now, one more thing, of course, before I show you on the breadboard. I am using a Texas Instruments BJT-based chip. And a BJT 555 timer, when it's giving a high output, does not give you the full voltage. Mine wants to give me about 4.3, which is about a diode drop. We've been through this before. And in the last video, I showed you how the datasheet tells me between VCC and out, there's just a resistor here in parallel. And by putting this resistor here in parallel, I get my full voltage when output is high rather than the 4.3 whatever. I still haven't figured it out. I thought it might be some sort of weird pull-up, pull-down resistor thing, but it's not. That's different behavior. I still have no idea. I'm very sorry. The moment I figure it out, I will very excitedly record a video on that topic alone. But until then, we're just going to say, hey, Texas Instruments knows what it's doing. It's a pity they don't pay me to say that. My setup is just as it was before, except different values now. So I've got my chip hooked up. I've got my standard 10 nanofarad, just like it recommends, nanofarad capacitor linking the control pin to ground. I've got a 1 millifarad, so 1/1000th of a farad as my capacitor, and I have a 2700 ohm, well, 2.7 k ohm resistor. Where is it? Over here. A 2.7 k ohm resistor as my R in the RC network. And over here I just have a loose wire. This is set up with a pull-up resistor over here. So this is my signal. Into trigger I have a pull-up resistor to high, and then I just plop this in, and that closes the circuit to 0, so that's my low signal. 1.1 times R times C in this case is 2 to 3-ish seconds. So it's large enough to see with a multimeter. So I will just turn my power supply on to 5 volts, because that's my favorite electronics number. I'll give it some current. So they're 5 volts. And now, right now it's reading low. This is the output. It's reading 0 volts. Oh, and I forgot to mention that mysterious resistor only for this chip. It's the same 10K I was using before. This is the one connected between VCC and out. So if I apply a low to trigger, it goes low and it counts, and goes back low. So we might say 1 1000, 2 1000, 3 1000, and it's about 3 seconds. And you can see if I go in and out, again, it still lasts about the same time. So 1 1000, 2 1000, 3 1000, and it's about the same time, even though I triggered 3 times during the interval. If I leave it in, 1 1000, 2 1000, 3 1000, and sometimes it wiggles, sometimes it doesn't, but it's staying high. I think without the extra resistor it wiggles, but it's pretty steady now. But if I remove the trigger, right now trigger is being held low. So I'm continuing to trigger it constantly after its interval ended. So I let go, and there you go. So what you have going on here is the threshold voltage has risen enough to turn the internal flip-flop off. But the trigger voltage is still low, which is low enough to turn the internal flip-flop on. If you recall from the SR latch video, I'm basically giving both set and reset signal at the same time. And what's happening is one of them is winning, but there's all kinds of different factors: electromagnetic noise, accidents in construction, everything, even trace lengths of wires can affect which one wins. This is an invalid state. This is not behavior you can count on. If you say, this, if I let it go and it immediately goes off, that works as I have it right now. And it's fairly likely this is a reasonable thing you can expect it to do, but don't count on it. For hobby work like this, if I was just making a circuit for myself, I wouldn't feel too bad relying on this behavior. But if I were making a component to be sold, then I would be slapped out of the business for doing that. This is invalid. If you have trigger and threshold on at the same time, that's bad. But if we just trigger it normally, then we have our timer that goes off right when expected. And that's all there is to it. So you can also use the monostable configuration for things like missing pulse detection. Let's say you have a pulse that's supposed to be continuously going and going and going, and you want to tell if it fails, like a safety feature in some sort of machinery. You can use the monostable to detect that missing pulse. You can use it as a frequency divider. You can use it as other things. And I may go into that in the future in other videos. But for right now, that's not terribly interesting. What is interesting is when you take the astable and the monostable, 2 555 timers connected together, one of them an oscillator, one of them this one-shot timer, together, and you get a little magic called PWM, pulse width modulation. It allows you to set the duty cycle of your square wave manually. So you can have your 50%, or you can have anything you want. You can even control it with a microcontroller. If you have something like a fan, and your fan is being driven by PWM, you can have a pair of 555 timers being driven by a pin coming out of your microcontroller, or a set of pins going into a DAC, digital to analog converter, whatever you want, and you just have a voltage go up and down, and you control your PWM, and you control your fan speed. But that is video 3. For now, I'll be seeing you.